Hey guys, so this is part 2 of the lecture over chapter 5.3 inverse functions. This part will be over the existence of an inverse function. So let's see what we have here. So the first thing we do to determine if there is an actual inverse function to find is we do something that's called a horizontal line test. So if you look at this particular graph here, you'll see that this graph, the one that's in black, what we do is we kind of take a few horizontal lines. We really only need one, but sometimes it helps to test a few just to see. And we sort of draw them through the graph to see if it hits the line at more than one point. And you see for this particular graph, it does. So you see where for x equals a and for x equals b, they both have the same y coordinate. So we can say that f of a equals f of b. And if a horizontal line intersects the graph of f twice, then f can't be 1-to-1. So just to kind of read this, we said the horizontal line test states that a function f has an inverse function if and only if every horizontal line intersects the graph at f at most once. So you see, since this horizontal line intersects this graph twice, then this function would not be 1-to-1, so it wouldn't have an inverse function. So, and then we get into the theorem. So theorem 5.7 of the existence of an inverse function, which essentially says a function has an inverse if and only if it is 1-to-1, and if f is strictly monotonic on its entire domain, then it is 1-to-1 and therefore has an inverse function. So these are both different ways to be able to tell. If one works, then the other one should hold. If one holds, the other one should hold as well. But these are two different ways to find out if your function does indeed have an inverse function. So with this one, remember, like we said, it wasn't 1-to-1, so it doesn't. But you see also, it's not strictly monotonic. Like when we say strictly monotonic, that means it's either strictly increasing or strictly decreasing. You can see right here, it's increasing, and then it gets to a point where it starts to change direction, and then it's decreasing. So since that changes, it can't be 1-to-1. And it having that change is what causes it to have this scenario where if we draw a horizontal line through it, it's going to hit it more than once. So if we move to the next slide where we have an example, if we get the function x cubed plus x minus 1, and so if we sort of draw it on a graph, sort of sketch it to see what it looks like, this is sort of what part of it looks like. And it looks to appear that f is going to be increasing over its entire domain. So you see this particular part is all increasing. So to be able to check it, we know that in calculus we can look at the derivative, which the derivative is just 3x squared plus 1. So the 3 comes down, subtract by 1, that becomes 3x squared, and then the x just turns into 1, and then the minus 1 turns into 0. So we have f prime of x equals 3x squared plus 1, which this particular function, remember, the domain of this is all real numbers. So then when you give this one the same domain of all real numbers, no matter what number you plug in, you're always going to get a positive number. And that's because this is always going to be positive, and then you're adding 1. So that's going to make it positive as well. The only thing this is not positive for is 0, but then you add 1, so you get 1. So this whole thing is always positive. It's positive for all real values of x. So f is strictly increasing, which means it's strictly monotonic. So yeah, this causes, since it's positive for all real values of x, that means that your original f is increasing over its domain. So it's strictly increasing. So f is strictly monotonic. And so by the last theorem, by theorem 5.7, we have that it must have an inverse function. Okay. So if we look at a different example, by basically taking another f where we just change this to a minus sign instead of a plus, if we draw that graph, you can see right here in this area, if we draw a horizontal line anywhere in this area, we can see that, for example, we have this one. If we draw this horizontal line, we see the horizontal line hits it in 3 different places. So it hits it at So if we plug in -1, we get 1. If we plug in 0, we get 1. And if we plug in 1, we get 1 as well. So it hits it in actually 3 different places. So it can't be 1 to 1. Now you may ask yourself, you may wonder, why does it matter that it's 1 to 1? Well, one thing you can think about is this. Remember, when we're looking at inverses, we're thinking about the key thing with inverses is that the coordinates flip in our points. So when we look at f inverse, for example, we would basically be saying that f inverse of 1 would go to not just -1, but it would go to 0 and 1 as well. So we have that f inverse of 1 would have 3 different outputs, which, if you recall, remember, a function, when you plug in an input, you can only get one output. You can't get more than one output. Otherwise, that doesn't make it a function. So you can always find an inverse, but it doesn't necessarily mean that that inverse is a function. And if it's not a function, then it's not really relevant to what we need. In order to be able to look at different things, we need it to be a function first. So that's why it's important to check the idea of a horizontal line test, being able to check that it's 1 to 1, things like that. Okay. And so for the existence of an inverse function, we look at the past theorem 5.7 to determine whether we have an inverse function. And then this just talks about solving for inverse functions. So you can solve for x to find the inverse function. You interchange the x and the y, and then you get the resulting equation that y is equal to f inverse of x. Right then and there, you want to be able to define the domain of f inverse as the range of f. So theoretically, you should already know what the range of f is, and you just call that the domain of f inverse. And then, of course, you want to be able to verify that the compositions both equal to x. That's how you would verify the inverses, as we did in the first part of the lecture. So for example 3, if we're looking to find the inverse function of f of x, we have square root of 2x minus 3. Notice that the domain of that function is is all numbers in the interval 3/2 to infinity, closed on 3/2, because if you plug in 3/2 you get 0, so this is perfectly fine to verify his. So when you look at the when you find the derivative, you can see that it is positive on its domain, because anytime you plug a number from this domain in here, it's always going to yield a positive number. So whatever number you get will be always a positive number. So f has to be strictly monotonic, and so we have that there must be an inverse function. And you can sort of see from the graph right here, this is the original graph, so you can kind of tell that it's increasing, but you want to be able to verify, because you really have no idea what goes on as we get further and further. So this kind of verifies the fact that it's just gonna kind of keep increasing at a steady pace. It's not gonna change shape or anything like that. So then to find the inverse function, we label this, we set it equal to y. Now we're going to solve for y. So the first thing we got to do is get rid of the root. We square both sides. We're going to subtract by 3. And then divide by 2. So then we get y squared plus 3 over 2. Now we're just going to switch the x and the y back. And then instead of writing y, we're going to write f inverse of x. And this is our inverse function. As you might have saw on the slide before with the graph, this is our inverse function. And you can see, as we stated from part 1, that they're reflections of each other over the line y equals x. Okay. Keep in mind the domain of f inverse. Keep in mind, so the range of our original function, if we look, is it starts pretty much at 0, it hits the x-axis, and then it just keeps going up. So since it keeps going up, our domain of this function is from 0 to infinity. So that way, when we talk about the inverse and the domain of f inverse, it ends up being 0 to infinity. We don't want, because if you look at the function originally, you think, well, why is it not all real numbers? We can plug in negative numbers. Well, the problem is if you start plugging in negative numbers, you get the fact that some negative numbers are going to also, when you plug them in, you're going to get, like, let's say you plug in 1. If you plug in 1 right here, then you get 1 plus 4, 1 plus 3, which is 4, 4 over 2, so that's 2. So f inverse of 1 would equal 2. But then if you plug in negative 1, you also get the same thing. You also get 2 as well. So then you get the fact that f inverse of 1 is equal to 2, and f inverse of minus 1 is equal to 2. Which, when you reverse it, you're getting that f of 2 is equal to 1 and minus 1, which means our original f wouldn't be a function. So that's why we're not using the negative numbers. We're just using 0 to infinity, which was the range of our original function. And then we can verify. So we have f of f inverse of x, and then we plug f inverse in for the x, and so we get the 2's cancel out, and then we get x squared plus 3, and then minus 3. The 3's cancel out, so we have square root of x squared, which is x, for all x greater than or equal to 0, because remember, this was the domain of our f inverse function. So this comes from the fact that our we were plugging in our f inverse function first. So if we switch the order, we have the square gets rid of the square root, the 3's will cancel out, the 2's cancel out, and we're left with x for all x greater than or equal to 3/2, which that was our domain for our original f function. Okay, so suppose we're given a function that is not one-to-one on its domain. We can always take a function, if it's not one-to-one originally, we can always restrict the domain to make it one-to-one. Or we can always restrict it to make it so that it's strictly monotonic. Okay. So show that the sine function f of x equals sine x is not one-to-one on the entire real line. Then show that if we restrict the interval from minus pi over 2 to pi over 2, is the largest interval centered at the origin on which f is strictly monotonic. So it is clear that f is not one-to-one because many different x values yield the same y value. So remember, the sine graph, if you sort of remember what it looks like, it's kind of like this cycle that's going on, this wavelength kind of pattern, if you will, where it always hits the same different values and over a period of time. So it just repeats. It just keeps repeating after a while. So you can tell just from looking at it that it can't be one-to-one. And so you'd have to pick an interval to decide which one you're going to pick to make it monotonic. So for instance, we have sine of 0 is equal to 0, but then we also have sine of pi is equal to 0. So moreover, f is increasing on the open interval minus pi over 2 to pi over 2 because its derivative f prime of x. So remember, the derivative of sine x is cosine x, and so cosine of x is always positive on this interval. And you can always think about it, if you were to go back and look at the unit circle, that's essentially, if you had the unit circle, you're looking at the first half of the unit circle like this, and so cosine is always positive on that side. So we have the left and right endpoints correspond to relative extrema of the sine function. You can conclude that f is increasing on the closed interval minus pi over 2 to pi over 2, and that on any larger interval the function is not strictly monotonic. So this is where minus pi over 2 hits, which for minus pi over 2 it's minus 1, and for pi over 2 it's 1. So you can see it hits its lowest down here, its highest, so it's minimum down here, its maximum up here, and then it's just increasing as we go from its minimum to its maximum. So that is the biggest interval that you can choose to where it'll be strictly monotonic. Keep in mind, you probably could have used another interval, so you could have started from pi over 2 to 3 pi over 2, and the only thing is you would have been going from maximum to minimum, so then its derivative would have been